Good evening, everyone. Myself, Chaitra Borkar, a Ph.D. scholar from IIT Delhi, and I welcome you all to the sixth live session of the NPTEL online course, Basic Principles and Calculations in Chemical Engineering, a course instructed by Professor S.K. Majumder from IIT Guwahati. So let's get started. I hope I'm audible. So, some information about these live sessions. These will be conducted every week on Tuesday from 7 to 9 p.m. For the duration of this course. The recordings of these live sessions can be accessed in our YouTube channel, and the links have been shared with you as well. The structure of these sessions is that firstly, we'll go through the overview of the lectures for the corresponding week and then solve some sample problems related to your assignment for the current week. So we'll start with the overview of the lecture 17. So lecture 17 was all about principles of energy. Firstly, what is energy? It is the ability to do work. It can either be converted or transferred. The transfer can be through flow of heat, mass transport, or performance of work. So as you can see from this GIF here, that energy is firstly in the form of potential energy here, and when it falls through this path uh, to a lower position, it gains kinetic energy here, and then kinetic energy becomes zero here. So that is how that is how energy is converted from one form to another. So the different forms of energy, as I've shown from this GIF, is that it can be kinetic energy, potential energy, or internal energy. Other forms may be such as nuclear energy, so energy stored in the nucleus of an atom, or thermal energy, or it can be radiant energy, so energy possessed by the electromagnetic radiations. So these are some other forms of energy. Main forms are written here: kinetic, potential, and internal. So kinetic energy is the energy possessed by an object owing to its motion. So formula for kinetic energy is given here: half into mv square. So m is mass of the object, v is its velocity. So owing to its motion, so a body in motion will possess some velocity. So this is how you get the formula for kinetic energy for a body in motion. Potential energy is the energy possessed by a body owing to its relative position to other objects. So m is mass, g is acceleration due to gravity, and z is the relative distance from some reference. Then we defined a system basically. The system is basically your object of focus which you need to analyze. And it is defined by a system boundary. So here we see, suppose this is some system. Ignore the closed system, but this is some system that we need to analyze. So it will have some system boundary, and only this region here is our object of focus. So whatever energy coming in, energy going out, mass coming in, mass coming out, uh, that we need to analyze in this system, in this region. So this is our system. So different types of system were also discussed. So closed system, open system, adiabatic system, isolated system, isothermal. So three systems are shown here. So a closed system is basically one which does not exchange uh, mass with its surrounding. However, it can exchange energy. So this is system, and anything outside of this system boundary is our surroundings. So the closed system can exchange energy with its surrounding. The open system can exchange mass as well as energy with its surrounding. The isolated system, however, cannot exchange any mass or energy with the surrounding. So there is no energy transfer or no mass transfer. Two other systems are written here. So adiabatic is such that no heat exchange. And isothermal is such that the temperature across the system is constant. So, the lecture 17 further discuss the principles of energy. So, in that, in the principles of energy, it further discuss the energy balance for a closed system. So, this is a closed system shown here. This is a closed system shown here. So, it can exchange energy, however, no mass can be exchanged. So, here we see that the change in internal energy plus the change in kinetic energy plus the change in potential energy equals heat uh, minus work. And same the energy balance for an open system is shown here. So it is rate of change in internal energy plus the rate of change in kinetic energy plus the rate of change in potential energy plus this PV work is shown here. So it is basically work, rate of work basically is can be defined as shaft work plus the flow work. So you can see here some some liquid or some fluid is flowing. So some mass is entering and some mass is coming out. So this flow work is characterized by this PV work basically here. Next we move to the lecture 18. So it discusses the laws and properties of thermodynamics. So this figure here basically sums up all the laws of thermodynamics. So it has zeroth law, first law, second law, and third law. So there are basically four laws. So zeroth law is about it gives us the concept of temperature. So it says that two systems in equilibrium with a in thermal equilibrium with a third system are in thermal equilibrium with each other. So if this is in equilibrium with this and this so suppose A is in equilibrium with B and C is also in equilibrium with B, so A and C will be in equilibrium with one another. Next, we discuss the first law. So it is about the conservation of energy. That energy can change forms but is neither created nor destroyed. The second law tells us about the entropy. So entropy of an isolated system always increases, and it gives us the direction of heat flow. Um, it moves from a hotter region to a colder region. And lastly, the third law. So it is about entropy of a system approaches a constant value as temperature approaches absolute zero. Next, we discussed about entropy. So entropy is defined for a reversible system. Mind you, this is for a reversible system. It is delta Q by T. So heat change upon or infinitesimally small heat change upon temperature. Then we discussed about the enthalpy. So enthalpy quantitatively is basically the heat content of a system. Or it gives us the measure of energy in a thermodynamic system. And you can write it as U plus PV, or H is the symbol for enthalpy and U is the symbol for internal energy plus the PV work. Or this term here is specific enthalpy. So this is basically H by M, H by mass. And same goes for U hat. U hat will also be U by M, and V hat is also V by M or specific volume. Then we discuss the calculation of enthalpy change. So firstly, we discuss the specific heat capacity Cp and Cv. So specific heat capacity at constant pressure and specific heat capacity at constant volume. So these are the relations for specific heat capacities at constant pressure and constant volume. So rate of change of enthalpy with respect to temperature at constant pressure is specific heat capacity at constant pressure. Rate of change of internal energy at constant temperature. Uh, no, rate of change of internal energy with respect to temperature at constant volume is specific heat capacity at constant volume. For mixtures, Cp mix is given using this relation. So if you're so basically the unit of Cp is either joule per mole Kelvin or joule per kg Kelvin. So if the Cp is expressed in joule per mole Kelvin, then this Xi will be mole fraction, mind you. And if it is expressed in joule per kg Kelvin, then Xi will be expressed in mass fraction. I hope this is clear. Then the change in enthalpy can be computed using this relation. So M Cp delta T. So T minus Tref. Tref is your reference temperature. So this will be delta T. And this holds true for when just a minute. This holds true for when Cp is constant for temperature range. Pref to T. Oh, sorry. Constant for Tref to T. So this temperature range. Okay. And if it is not constant for the said temperature range, then we have a differential form of Cp in terms of temperature, and then we integrate this Cp dt from Tref to T, and this is the mass rate. So this is basically the enthalpy rate, and same goes for the change in internal energy. We can find it using this relation. Further, in lecture 18, we discussed the enthalpy of mixing. So for ideal mixtures we have discussed in the previous lecture that ideal mixtures or ideal solutions, the particles don't interact with one another. So enthalpy of mixing for a ideal mixture is basically equal to zero. So change in enthalpy of mixing basically. So the enthalpy of mixing can be enthalpy of the mixture can be expressed as the summation of the mass fraction into the specific enthalpies. So we can express it in that way. Then for non-ideal mixture, however, we can express the enthalpy of mixing for as U mix plus delta PV mix, which will be uh, delta U mix again plus P delta V mix. And V mix is given using this relation. So the volume of the mixture may not be equal to the summation of the volume of the individual components. So that is how we get the delta V mix for non-ideal mixtures. Again, this delta V mix for ideal mixture will be equal to 0. And the change of internal energy of mixture is given using this relation. We move on to lecture 19, which was all about standard heat of formation. So heat of formation for no phase change. is given using this relation. So change of enthalpy with chemical reactions. So this is the heat of formation, and this is computed experimentally minus T ref to T CPDT. And standard heat of formation is defined as the enthalpy change associated with the formation of 1 mole of compound at 25 degrees Celsius, 1 atmospheric pressure from its elemental constituents. So basically, C plus 2O, basically C plus 2O giving CO2. So that is, this is the reaction for formation for CO2. So if the whatever the enthalpy change comes out from this reaction is the enthalpy of formation for CO2. So enthalpy change for phase change is given using this relation. So to this previous term, we add another delta H specific enthalpy change at the constant temperature and pressure, and this owes to the change of phase term. So here we see that in this, sorry. So here we see that suppose there is a solid and you increase its temperature and you keep increasing its temperature, and at one point it converts to liquid. So when it converts to liquid, the temperature remains constant. However, the heat energy keeps on increasing. Then when it becomes liquid, you keep increasing its temperature. It is still liquid. It is still liquid. However, the temperature is increasing as well as the heat content of that system is increasing, which is characterized by NCP delta T. Then at some temperature, it changes its form from liquid to gas. So at that point, the temperature remains constant, the heat energy keeps on increasing because this is the addition of latent heat. And then again in gas, you can keep on increasing the temperature. So that is how you understand the heat content can be either through the sensible heat or the heat content can be through the latent heat, which is at a constant temperature, which is due to the phase change. So we now will solve the some sample problems. So we start with the first question. The first question is energy is the rate of doing work, ability to do work, both A and B, or none of these. So what will be the correct answer here? Can anybody tell me the correct answer? What is energy? We have just discussed this. So as I have discussed this before, energy is basically the ability to do work. So correct answer is B, B option here. Rate of doing work is, what is rate of doing work? Power. Next question. The correct dimension of work is, so what is the correct dimension of work? So as we know, work is basically force into distance. So when we apply force on a body, it moves a distance. So that is what we call as work done. So force, the dimension of force is ml t minus 2. How do we get that? Force is mass into acceleration. So mass will be m, acceleration will be distance upon time square. So L T minus 2. So that is how we get it. And D is basically L. So the dimension for W is ml2t minus 2. So the correct option here is C part. Next question. Third question. Energy can neither be created nor be destroyed. I guess this is correct from the first law. Flow from one body to another. Again, this is correct. Can be converted from one form to another. Again, correct. All of the above. So the correct option here is D part. Match the following. So we need to match the form of energy with its example. So here we see what will be the example for kinetic energy. Will it be a stretched slingshot, a running child, a working toaster oven, or a radio wave field? So I guess the correct option here will be the second option in the right column. So because kinetic energy is the energy possessed by an object owing to its motion. So a child running will have some velocity with it, so it will possess some kinetic energy. Next, next part is potential energy. So I guess the correct option here will be stretched slingshot, because when a slingshot is not stretched, it is at rest, and when you stretch it backwards, it will possess some potential energy with it, and that potential energy will be another form of potential energy, elastic potential energy, and when you release it, it will possess some kinetic energy. So the correct answer here for the potential energy is a stretched slingshot. Then radiant energy, the correct answer for this is a radio wave field. So radiant energy is the energy possessed by the third electromagnetic radiation. So a radio wave is an example of an electromagnetic radiation. Then for electrical energy, obviously the correct answer will be the third option in the right column, a working toaster oven, because it operates on electricity. So the correct answer here will be A2, B1, C4 and D3. A2, B1, C4, D3. B part. Next question. 1 kilowatt hour is equal to how many joules? So we can compute this using this logic. So 1 kilowatt is equal to 1000 watts. Now I can say 1 kilowatt hour, sorry, 1 kilowatt hour is equal to 1000 watt hours. Now 1 hour is equal to how many seconds? 3600 seconds. So you can put that here. So 1 kilowatt hour is equal to 1000 into 3600 watt seconds. We know joule per second is watt. So joule will be watt seconds. So this is how we get 1 kilowatt hour is 3.6 into 10 to power 6 joules, because this watt second is joules. So the correct answer here is the D part. Next question. Refer to the following figure and calculate the kinetic energy rate of water flowing through a pipe. Assumed density of water is 1000 kg per meter cube. So we know the flow rate is 0.02 meter cube per second, and the diameter of this pipe is 0.2 meter. So firstly, we know what we know, we'll write here. So flow rate Q dot, volumetric flow rate, mind you, point zero, sorry, meter cube per second. We know the diameter of pipe which is, or we can write it as D. So that is 0.2 meter. So all are in SI units here up till now. And row of water or density of water, 1000 kg per meter cube. So we know volumetric flow rate, we know density of water. So we can find out mass flow rate, right? So mass flow rate will be m dot q dot into rho w. So 0.02 into 1000. So that will be 0.02, mind you, not 0.2. 0.02 into 1000. So that will be 20 kg per second. How I got kg per second? This is kg per meter cube. This is meter cube per second. So meter cube get cancelled. We get 20 kg per second as mass flow rate. So we need to find out the kinetic energy rate. So what will be the kinetic energy rate? Ke dot will be m dot, half m dot v square. So we know m dot here, but we don't know v or velocity. So how can we find that out? We know the volumetric flow rate and we also know the diameter of the pipe. So volumetric flow rate, we can say that it is equal to V into AC, or just a minute. V into AC. What is V? V is velocity and AC is area of cross section. So that will be equal to V into pi d square by 4. So V comes out to be Q dot by pi d square by 4. So 20 into 4 upon pi into 0.2 square. So that will come out to be so velocity comes out to be not 20. Just a minute. Not 20, it will be 0.02. So it will come out to be 0.6336. Oh, sorry, 6366. 0.6366. What will it be? Velocity, so meter per second. So this is meter cube, and this is meter cube per second, and this is velocity is meter per. Just a minute. This is meter cube per second, and this is meter square. So meter square gets cancelled from meter cube, so meter per second. Yeah. So velocity is 0.6366 meter per second. Then now we can calculate rate of kinetic energy. So half into m dot is 20 into 0.6366 whole square. So it comes out to be roughly 4.0526. So 4.05. What will it be? Joule per second. So kinetic energy is in joules and rate of kinetic energy will be joule per second. So the correct option here is B part. Next question. Match the following again. So you need to match the types of system with its definition. So what will be the correct answer for isothermal system? Can anybody give me the correct answer here? The correct answer for isothermal system is that the same temperature throughout the system. Second option again. Then for closed system, we have discussed this. Anybody? So the correct answer here is the first option in this right column. Only energy transfer across boundary. Now isolated system, we know that no mass and energy transfer across boundary, and for open system obviously the third option in the right column, both mass and energy transfer across boundary. So again the correct answer is A2, B1, C4 and D3. A2, B1, C4 and D3, again B part. Next question. First law states energy can neither be created nor be destroyed. Again correct. Energy of a system is conserved. Yes, correct. Energy can be converted from one form to another. Again, correct. So the correct answer here is all of the above. Next question. Calculate the enthalpy of the gas based on the following data. We need to calculate the enthalpy of the gas. We know the molar volume. We know the specific internal energy of the gas and assume the atmospheric conditions prevail, that is T is equal to 25 degrees Celsius, temperature is equal to 25 degrees Celsius and pressure is 180. So we know that if we need to calculate the enthalpy and we are given internal energy, so we need to only add the PV term to it. So we know the specific internal energy of gas. So we need to calculate basically the specific enthalpy, which is in terms of joule per mole. So this will be H cap, U cap, P, V cap. So we know the specific molar volume as well. So V cap is 50 liter per mole. So this is not in SI units. So 1 meter cube, sorry, 1 meter cube is equal to 1000 liters. So 1 liter will be, just a minute, my bad. So 1 liter will be 1 by 1000. So 0.001 meter cube. So 50 liters will be V cap will be 50 into 0.001 or 10 to power minus 3 meter cube per mole. So we get this in SI units. Now pressure is 1 atm and pressure we can write as P is equal to 1 atm is equal to 101,325 Newton per meter square or 101,325 pascals. So this is in SI units. So we just need to put this here. So U cap we are given is 2000 joule per mole. This is in SI units. Plus I'll write it here 101,325 into V cap we know 50 into 10 to power minus 3. So the correct answer will be 7066.25 joule per mole. The correct answer is A part. Next question. During phase change, the temperature does not remain constant. So phase change is the heat content of that phase change system is characterized by latent heat, and at that phase change the temperature does remain constant, as I have discussed with you before. So this is a false statement. Enthalpy is heat content of a system. Yes, it is a heat content of system, correct option. Then measurement of energy in a thermodynamic system. Yes, correct again. System's internal energy plus the product of volume and work, again correct. So all of the options above are correct. So correct answer is D part. Next question, the enthalpy of mixing for ideal mixture is equal to unity. No, it is not correct. This is a false statement. As the enthalpy change of mixing for an ideal mixture is zero, because then we can compute the enthalpy of the mixture as the summation of the product of mole fraction into the specific enthalpy. Next question, what is entropy? Entropy is heat content of system? No, that is defined by enthalpy. Degree of withstanding temperature change? No, not correct again. Degree of randomness, yes. Entropy is defined as degree of randomness in a system. Degree of orderliness, which is the inverse of this, so this is also incorrect. So the correct answer here is C part. Next question, select the correct correlation between specific heat capacity at constant pressure and constant volume for ideal gas. So the correct answer here is Cp is equal to Cv plus R. Next question, a stream of nitrogen flowing at 200 kilomole per hour is heated from 323 Kelvin to 373 Kelvin. Calculate the heat transfer in kilowatts. Heat one hint, sorry, 1 joule per second is equal to 1 watt. The CP standard specific heat capacity at constant pressure and at standard condition for nitrogen is given using this equation. So these are the coefficients for the CP term, a different coefficient. This will be A, this will be B, this will be C, this will be D. So basically we need to compute the heat transfer. So heat transfer again can be computed as MCP dt, T ref to T, M dot. So Q dot, or we can write capital Q dot. Okay. So we know M dot in kilomole per hour. We we convert it to kilomole or mole per second basically. So it will be, sorry, per hour. So 1 hour has 3600 seconds. So upon 3600, so oh sorry, mole per second. So that will come out to be 200 into 10 to power 3 divided by 3600. So that comes out to be 55.55 6 mole per second. So this comes in SI units again. Then we need to compute this integral term. So firstly, this will be Q dot is equal to 55.556 into, now T ref we are given all in Kelvin. Mind you, the temperatures need to be in Kelvin. So 323 to 373, we know Cp. So 29.5909 minus 5.141 into 10 to power minus 3 T plus 11.1829 into 10 to power minus 6 T square minus 4.968 into 10 to power minus 9 T, T3 into dt. So we need to integrate this and then apply this limit. So this will come out to be 55.556 into, if we integrate this is a constant term, so the integration it will be 29.5909 T. And if we apply the limit, 373 minus 323. The integration of T is T square by 2. So minus 5.141 into 10 to power minus 3 divided by 2 into 373 square minus 323 square. Then this third term 11.1829. So the integration of T square is T cube by 3. And if we apply the limit, it will be 373 cube minus 323 cube. And then minus, again one more term. So it will be 4.968 into 10 to power minus 9 upon 4, because the integration of T cube here will be T4 by 4, T to power 4 by 4. And if we apply the limits, it will be 373 to the power 4 minus 323 to the power 4. We need to compute all these terms. So Q dot will be, we firstly compute all these terms. So 55.556 into 29.5909 into 373 minus 323, 1479.545. Then the next term, negative 5.141 into 10 to power minus 3 divided by 2 into 373 square minus 323 square, again 89.4534. Next term is positive 11.1829 into 10 to power minus 6 divided by 3 into 373 cube minus 323 cube. So 60 positive term 67.831 and minus last term 4.968 into 10 to power minus 9 This is not -4, this is minus, sorry, just a minute. Hmm. So it will be divided by 4 again, and then into 373 to the power 4 minus 323 to the power 4. So this comes out to be 10.522. 523. So if we compute this, so this comes out to be 80,411.732. This is mole per second. This is joule per mole per Kelvin into delta T. So this will be joule per mole. This is mole per second. So this will be mole and mole get cancelled, joule per second. So we need to calculate in kilowatt. So this is basically, we can write this as watt. So kilowatt will be 80.41 kilowatt. So the correct option here is D part. Okay. Next question. Calculate the standard heat of reaction for the reaction NO plus half O2 giving NO2. So we need to compute the standard heat of reaction. So what will be the standard heat of reaction will be the nu I into delta HF naught. And this nu I will be positive for products and negative for reactants. So we can compute, and the heat of formation for O2, because it is in elemental form, it will be 0. So heat of reaction for this reaction can be computed as de, delta HF NO2 minus delta HF NO. So that will be 90.4 minus 33.85. That will come out to be 56.55 kilojoule per mole, same units. So the correct answer here is B part. Suppose if this equation was written as twice of NO plus O2 giving twice of NO2. So how will you compute the heat of reaction then? So it is basically the twice of this reaction equation here. So we will have this is the stoichiometric coefficient. So 2 into 90.4 minus 2 into 33.85. So basically twice of this value. So this comes out to be 113.1. So this is twice of 56.55. So suppose if this equation was given in this form, then the heat of reaction will be 113.1, which is twice of whatever value we have calculated for this. Any questions? Anybody? I hope you understood everything what I have told you up till now. If there are no questions, I'll go ahead and close this session for today. Thank you everybody for joining.